Thank you all for coming in. This is Chetan Trivedi. I'm head of AI and Big Data at Verizon Media Group. So how is everyone doing so far? Okay, thanks. So I'm going to mainly talk about the Verizon AI solutions, machine learning use cases. So some of the use cases that are listed here, these are all handpicked, and that covers like cellular network performance prediction, threat detection system, traffic prediction, and IoT anomaly detection use case. So brief history on the cellular network performance prediction. So basically, Verizon has multiple cell towers in different geographic locations, and what is happening is like you have the cell towers which has an antenna and the base station. Now we are collecting like multiple parameters on a daily basis from those base stations, and what we are trying to do is like those parameters are impacting some of the key KPIs or the quality of service parameters, such as barrier drop, SIP, and handover failure. So that can cause for someone to lose the connection while he's on the phone or he's trying to transmit the data. So basically that's the genesis of what we are doing here. So briefly, the market size is $9 billion. Now, this is a global market size, and we are not saying like Verizon is making like $9 billion here actually, but it's a overall size for the particular use case where we are trying to save money for the company, or we are trying to retain the customers because of the superior performance of the network. And so that's the genesis here. And what we are trying to solve here is a couple of key things on optimization of the base station parameters. So how do we optimize the base station parameters in a best possible way? So current way of doing things is more like a manual way of doing, where there are network operators, they make the random changes to the parameters and they try to bring those KPI values in bound actually. And but there are like there are possibility that there are a lot of errors actually in doing that manual work. And the other thing is like, how do we best predict the base station parameters? So here what we are trying to do is like, how do we predict it for the next day or the day after actually? So that way it's fully automated by using AI/ML concept. So briefly, the data flow is some of the key features that we are trying to use. And there are many more features actually. These are not the only features, but some of the key features are indicated on the left. E-node sector carrier, parameter name values, and KPI data. So KPI historical data values are very, very important here, because we are trying to take in the historic values and try to predict the new value. And so basically output on the dashboard will be more like a predicted KPI value, and those values will be for those KPIs that are highlighted here: barrier drop, SIP, and handover failure. So current use cases are just focused on these three values to be predicted. Now, in the middle block, actually, we have the platform. This is more like a big data platform that is collecting all the data from different base stations. And what it is doing is like it's doing the regular data processing stuff and doing the supervised learning and regression algorithms. So I'll deep dive into the middle block here, actually, which is of more use to all of you here. So what it does is like we have several regression algorithms that are tried and tested. Some of them are like linear regression to gradient boosting algorithm to random forest. So some of the new algorithms that are coming as well actually that have been tried here. And the best model is selected. We do the standard stuff actually, train the data set and come up with a predicted value. And we compare the model outputs and see which one is behaving the best. And so far, the model has predicted the best value is like 0.11, which is the mean absolute error for the regression model. And we are still working on it actually, and still under the process to improve it even further actually. So what we are trying to do is like we want to minimize the error as much as possible to make sure that our model has the best value possible. And this is to give you the idea on how the antennas and their locations, they look actually, this is geofenced by a certain region, and the way it is shown here, it's like basically the current 4G LTE antennas are like 3-leaf pattern actually that you can see here, and the ones with the circle are more like a omnidirectional antennas, which were more like a old. But here the idea is like on this UI, you will be able to see all the optimized parameters actually once the model output is shown. This is the UI actually. This is one of the UI screenshots. There are many other screens where you can see the optimized value that is the output of the model actually. So at this point, I would like to switch gears and would like to move on to the next use case. This is more in line with the threat detection system, and I'm specifically focused on the DDoS use case, which we worked on. DDoS is a distributed denial of service, and this particular scenario occurs where multiple machines, or you can call some people call it like bots as well. So multiple machines are trying to attack a particular IP address or a site and make that particular website as non-functional. That's the use case that we are trying to address it here. Again, the market size is the global market size. It's a $50 billion market. This is a global number actually. It's not something that Verizon makes out of this. But here, what we're trying to address is a couple of things. How do we best detect the threat in real time when it's happening? And the other thing is like, how do we mitigate the threat actually? Similar data flow here. What we are trying to show on some of the key features are source and destination IP address and the destination ports. And also you see that IO bytes and packets and the source IP counts. So source IP count is a very important feature here because multiple sources are attacking a particular IP address, and that's the reason is one of the key features here. And the output you see is mainly anomalies that are detected by the model actually, which is by router and by an interface. So if I am a security analyst, I would like to know like which particular router and or interface is compromised or has a threat. It can be a potential threat. It may be sometimes it's a false positive as well. So we have to make sure that our model is so accurate in a way that it's trying to mitigate the false positives and trying to reduce those numbers. And in the middle, we see that it's mainly time series data and ensemble learning. Those are the key things that we have used here. And so I'll deep dive into the middle portion. So basically, it's a time series data. What we are doing is like we are collecting the data from networks and routers. And these data collected under the data agreement with the particular customer. So customer comes to us, we have the contract in place, and they are giving us the permission to collect the data from their assets. So it's not that something that Verizon collects it without the consent. So it's with all the proper data agreements in place, we start monitoring the network and the router for that particular customer and for those assets actually. And the data sets basically are coming at a different intervals. So one is the SNMP data, which is a network data, and there is something called net flow, which is more like a periodic one minute data. So every 1 minute the data is coming. And this data is labeled. So basically we know that on a given particular day, because this is like based on the past attacks that have been in the system, those are flagged and labeled as an attack. So it's more like a supervised learning that we are trying to do here. And it has a real-time threat detection capability and ensemble learning. So here, what we are doing is like, since there are multiple workflows, so basically there is a network data and router data, and we have the classifiers in both the workflows. What we are trying to do is like the classifier, we are trying to take the vote from those multiple classifiers and trying to declare it as whether it's a real threat or not actually. That's the reason we implemented the ensemble learning here to make it more robust. And this particular system has detected all the major attacks so far. So So model is doing like great so far. So it's like really doing the job here. And this is one of the attacks that I have depicted here, which was on a particular given day. And what you see is like, you will see that the packets are going high actually. So the key features, as I mentioned earlier, there is input bytes, output bytes, and input packets, output packets, and also the ratio of those two. So based on that, actually, we see that when the packets are going high, that means that there is like a lot of activity going on, and that this is a potential threat, right? And so that's what is depicted here. This is a screenshot of one of the typical UIs that any cybersecurity analyst or network analyst will see. On the left, you see is a list of routers. Gateway router and broadband router, and on the middle panel you see the interfaces that are vulnerable or under the threat, and on the right side you will see the key features by which we declare it, whether it's a real threat or not. Actually, those are bytes and packets on the right side. So at this point, I will switch again. I'm switching the gears too quickly here, but I'll give some opportunity at the tail end actually to ask some questions. So the third use case is done. For this, the whole genesis of this is it's a traffic flow detection. Verizon has a tie-up with multiple cities throughout the United States and also outside. And what we are trying to do is like we are trying to focus in a specific area where we are trying to detect the traffic flow and or congestion patterns on a given intersection or the street. And the way we are doing, I will explain how it is done. So basically, again, this is a global market size of $27 billion. The number is very conservative. There is more potential here. And there are few things that we are trying to address here. One of them is a traffic flow monitoring. So that's the key requirement from the cities, that how do we best possible way we monitor the traffic at a given particular intersection to reduce. So eventually the application is like basically they want to minimize the commute hour time and congestion and avoid the fatalities that are coming with high speed and things like that. The second aspect is the vehicle speed, which contributes highest to the fatality caused to the pedestrian or to the bicyclist. And also the third one, which is the safety of the pedestrian and the bicyclist. So these are the three key things that we are trying to address. Here also, briefly, the data flow, the way it works is like there are multiple video nodes that are mounted on a particular given intersection or the street in the city. And it's collecting the key information. There are many other parameters, but these are the key parameters that we are collecting: vehicle speed, location details, vehicle count, and pedestrian counts. These are all captured by the video node that is mounted, and that comes to the platform. The platform has two components. There is image processing going on, and also there is anomaly detection at the tail end. And also the dashboard will show the vehicle count and max and average vehicle speeds, because the speeds are the key parameter here, which will give us the insights on whether how we can prevent more fatalities which are caused by the vehicle speeds. So the image processing and anomaly detection actually. So traffic flow activity is captured in real time by multiple video nodes and uploaded to the platform. And what it does is like there is image processing going on. So there is the slices of video are taken and converted into some images. From those images, they are trying to detect the object and how different objects are being recognized. It can be a pedestrian, bicyclist, automobile, or a pet. And so multiple objects are detected, and that's the key. And that information is also sent to, along with other information, is sent to the anomaly detection model actually, which is collecting the key attributes and making the determination on the anomaly, whether on a given time or a given day is that an anomaly or not actually. And so process data is fed to the model, and anomaly is detected by this particular anomaly detection system. And based on the detected anomaly, CT personnel can assess on the dashboard and see whether, and make a judgment call on whether he wants to optimize the timings of the light on a given intersection, or how does he fully manage the traffic flow in and out of that particular intersection. And so this is one of the screenshots. There are multiple other screens, but one of the key screenshots is where on the left side you see there are multiple video nodes. All the video nodes you can zoom into it, and so this is one of the video nodes which is highlighted here on the left. And you can see the average and maximum speed on the right, which is at a particular given time, which is 12 p.m. And you down below you see the heat map of vehicle count on a given hour actually. And you can do it for the entire week and for the entire month actually. So this is how a traffic person or the person who is doing the analysis on this traffic can determine whether he needs to adjust anything here in terms of the traffic light adjustments or any other things that he can do or take remedial action to make it more free flow and smooth. And the last one is IoT anomaly detection. So the IoT anomaly detection here, the IoT device is an intelligent vending machine. So Verizon has a tie-up with vending machine partner actually, and what we do is like basically again under the data agreement they are trying to send the data to us. This is a network level data, and the goal is to detect and identify whether there are machines, few machines or many machines or IoT devices that are healthy or unhealthy actually. So that's basically trying to identify the anomaly and see whether these are anomalous devices. Now, those are flagged by our model as anomalous. Doesn't mean that it is really anomalous, but we are trying to minimize the false positive by making sure that our model is like really robust and tries to detect and minimize as much as possible on the false positive side. So here, $12 billion global market size for the intelligent vending machine space, and we are trying to address some of the key things such as device anomaly count. So at a given point in time, if IoT analyst wants to know how many of his vending machines are anomalous. So basically they are either functioning but not fully functional, or there are some anomalies actually in one category or other. There are multiple categories such as network, RF, and there are many more categories by which we are declaring it as anomalous or not. And so that's where the middle block comes in, where anomaly types. So what category or what type that particular device is anomalous. So accordingly, he can take the remedial action based on what category it is. And the third one is anomaly severity. I would like to know whether it's a critical, high, medium, that kind of severity levels. So based on that, he can determine whether to take action now or later. And brief data flow here again: input, output bytes, connection counts, disconnect code, and active and session times. And also on the output side, we have the anomalies which are by category: network, RF, data usage, and others. And basically what we are doing is in the middle, the platform is again a big data platform. We have the unsupervised learning because the label data set is not available. So as and when the data, new data points are coming, we are running the clustering algorithm on top of that and making sure that we group the devices by their behavior. And so that's how we are doing the clustering on top of that. And so as I mentioned earlier, critical network data comes to the platform, and scalable machine learning algorithm, which is in this case unsupervised learning, it runs on a collected data set, and then group of devices are being clustered based on their behavior, and that's how it's doing the work. And fine-tuned model is deployed in production at scale, and it's trained periodically. So basically, you have to keep the model training and make sure that it's more relevant and it's not like completely out of date actually. So to make sure that it detects and minimizes the false positives here. And this is the brief screenshot. What we see here is 0.12% of the devices are anomalous at given point in time, and they are identified by categories at the bottom, and also they are declared as critical, high, medium, low. So basically you see here, and in the middle you are seeing like by hour on a given day. So this is a real-time information that IoT analysts can see and take a remedial action right away actually based on what he's seeing on the dashboard. So it's like really helpful to take any quick action to make sure that, because otherwise you're trying to avoid the loss of business here, and so that's the goal here, to make sure that that we take a quick action on this one actually. Thank you all.